Thanks, Chris. Thanks, Pierre. Thanks, everyone, for joining. It's a great pleasure to speak to you today. Sorry I couldn't make it to Northwestern. The journey would have been quite long. I'm Robert, Product Manager for Electron Diffraction at Rigaku, located in Frankfurt in Germany. And I'm honored to speak to you today, focusing a bit on a development topic we're following quite a lot at the moment in Rigaku, which is high throughput techniques for electron diffraction and all kinds of automation, which will enhance the scope of electron diffraction quite a lot, we think. But let me first start with some fundamentals of electron diffraction just to get us all on the same page. So, of course, you will all be aware of the fundamentals of single crystal diffraction in a most simple way. Well, you shoot mostly X-rays, sometimes neutrons, on a crystal, rotate the crystal, record the black spot intensities, computationally get phases to Fourier transform this into an electron density and build a molecular model into it. Well, that's well established and everyone knows it. Now, if you use X-rays for this, the signal you get arises from elastic scattering of X-rays from the electron density in your specimen around the atomic nuclei. Now, if we replace the X-rays in this scheme by electrons, what will happen is that they will interact not with the electron density, but the electrostatic potential inside the sample. One consequence of this is that you get a signal that depends much more also on the nuclei than on the electrons. Won't go into too much detail about this today, only a little bit. But the key differentiator here is that this process is roughly 5 orders of magnitude stronger, but depending on what atom, than this one. So if you have electrons, you can access crystal sizes that are below 1 micron easily because they will still give you enough signal. On the other hand, they should not be larger than around 1 micron because then they will essentially become a beam stop because of the strong interaction. A more subtle but as important point is that for each useful diffraction event, for each useful elastic scattering event, which will give you rise to diffraction, you always pay the price of some radiation damage, which your sample will suffer. And for each of those elastic interactions, you will pay a much higher price with X-rays. You get roughly 3 orders of magnitude more energy deposition for each event than you will get from electrons. And this is another reason why you can get structure from these nanocrystals with electrons before actually making them explode, like you would, for example, in an X-ray free electron laser. So if we use electrons in these schemes, the crystals are smaller, and you measure a different quantity at this step, the electrostatic potential, which in the same way allows you to build a molecular model into this. And this distinction is something that's quite interesting, but we'll only briefly go into this today. Now, let me talk a bit about what happened in electron diffraction in the last 15 or so, maybe 20 years, and why we have seen such a surge in interest in electron diffraction. So when 20 or so years ago, people would think and talk about electron diffraction, what this usually referred to was this classical ED as it is done in electron microscopy, where you tilt your specimen crystal such that you excite a low-lying zone axis like this, discrete zone axis. This is actually the Ewald sphere, which is almost a plane for electrons due to the short wavelength. And because of that, what you will get are those highly regular two-dimensional diffraction patterns. And one characteristic of this is that because of the strong interaction and this geometry, which excites a lot of regularly patterned spots at once, you get very strongly dynamical intensities because of multiple scattering. So for each of those black spots, the electron can end up here through a multitude of different pathways of partial beams. And that means that our favorite relation in crystallography, which is that the intensities are related to the square of the structure factors, is totally broken in this scenario. Still, it has been shown that it's possible to solve structures from this data. This has just been not really recognized a lot, especially in the 1960s by Weinstein in Moscow. Well, the big paradigm change came with the realization that you can get much better structures and a much more straightforward solution technique if you do not do this, but do it rather like in crystallography, where you randomly, or actually not randomly, but in a tomographic way, tilt your crystal in, for example, discrete steps not aligned with any zone axis. In this case, you get weaker excitation of these reflections and the less regular patterns, and the intensities approach a much more kinematical nature. So this becomes still not equal, but at least gets more approximate. I think there'll be another presentation about this topic and much more in depth. But this was, let's say, the key realization made in a small molecule world, for example, by the group of Ute Kolb in Mainz, and in the protein world in the US by the group of Tamir Gonen in the late 2000s, early 2010s. And this is what really kicked off this modern electron diffraction. This was then just a bit later enhanced by adding precession to this, beam precession, which then integrates over these reflections fully and gives you even better intensities and further reduces dynamical effects. It's still a state-of-the-art technique, especially for radiation-hard samples and heterostructures. And then the final evolution step, which is mostly used these days, is continuous rotation. It's basically like in a modern X-ray diffractometer. You put your crystal on a goniometer, rotate it continuously, collect data continuously. So what you then see is really this full evolution from this old school discrete zone axis all the way to something where you rotate your crystal continuously, collect continuously. This is a very fast, very dose efficient process. The data quality is very good. And the data you get is almost kinematical, so you can use standard techniques. So to put this into context of X-ray techniques, well, I mentioned already this. With single crystal X-rays, you always have this roughly 1 micron barrier. So you can collect from visible crystals, one could say. With powder XRD, of course, you're not restricted to this. You can use the tiniest of crystallites, that's fine. But you only get integrated information, which is much more limited. As you will all know, getting structures from powder data is tedious. You need to factor in a lot of, let's say, ugly circumstantial effects and so on. And now electron diffraction in a way sits in between the both, or marries aspects of both, in that it is a single crystal technique that operates on single grains within a powder and combines aspects of both in that regard. So what do we need from such a sample if to do electron diffraction? Well, with some exceptions that I won't talk about today, we want them to be crystalline, right? So if you have a powder pattern like this, electron diffraction won't save you either. You need something that will give you some spots. Now, the particle size is typically the range from 10 nanometers to 2 microns. If you see this under an optical microscope, don't do ED, just get a single crystal X-ray machines. And then if you see something that looks still a bit grainy under an optical microscope, you have a good chance that you have crystallites that are small enough. If you have a SEM, you can just check the size and then get some excellent information. What's not strictly required, and it's actually something that can be even a strength of electron diffraction, is the samples don't have to be pure or have a known composition. What phases are in there is not necessary to know. You don't have to know solvent contents, you will find it out. And against the popular conception, they even don't have to be particularly radiation hard. Electron diffraction can be very, very gentle, much more so than electron microscopy, for example. So just briefly on the workflow, you put these powders on grids that look like this, TM grids, 3 millimeter in diameter typically, coated with a carbon film. Put this into your diffractometer or TM. In the TM, you screen for the crystallites. This circle has roughly 2 microns in diameter, and search for good looking ones. And then from each of them, you collect a full diffraction data set, typically within less than 2 minutes for each of them. And you get the structure. That's how it works in a nutshell. But there's another aspect to it, and that is, as I mentioned already, you don't have one grain on a grid, of course. You have thousands, 10,000s of grains per grid, even if you have only less than micrograms of samples. And this powder can, in fact, be totally polyphasic, impure. You can have all sorts of dirt, precursors, whatnot, catalysts in there. And you measure it grain by grain. So you can tell the machine now, look at each of many grains sequentially and get me the structure out of it. It can be in a pharma application, for example, a grounded pill. It can be a raw synthesis product. And you will just understand what's going on, even in cases where a powder XRD pattern will just be a convoluted mess and you have no idea what's going on. And this already foreshadows a bit why automation is so important, and I'll talk about this later, of course. So, important thing to keep in mind, micro-ED is not only a single crystal technique, it is also a powder technique where you study grains on an individual level. So, just to recap, in micro-ED or 3D ED, you replace X-rays and single crystal diffraction by electrons. The modern scheme has been developed in the 2000s and 2010s by just doing it like with X-rays, rotating crystals freely. Dynamical diffraction effects becomes manageable and structure solution becomes straightforward. And by now it has been applied to pretty much everything that's crystalline, including proteins, even though I won't talk about this today, a lot of different materials. And so far, the adoption of this technique has been a bit slow also because you needed an electron microscope, and even more, you needed a research group which is skilled in very well, both in electron microscopy and in crystallography. And this is fairly scarce. Now, this has changed radically now that dedicated instrumentation for micro-ED becomes available, where TEM knowledge is not needed anymore. And this brings me to the next section. So how does this actually work practically? Things to keep in mind for X-ray crystallographers who have never worked with ED. Well, first of all, these nanocrystals are obviously invisible to light. So you cannot screen them under light microscope. You have to do the screening inside the diffractometer. Then electrons will just not pass air because they interact too strongly with the gas. So you need a sample transfer system into the vacuum of the diffractometer, and you need to protect your samples against degradation due to the vacuum, especially for solvated or hydrated samples. The radiation doses to extract full diffraction information from these small crystals are very high. So you need the best possible detector you can think of that doesn't waste radiation on poor detection. So you don't want any sort of background signal. You need extreme sensitivity, and you need to make sure that your instrument controls those in a very reliable and calibrated way. And then, as I mentioned already, you have thousands of crystals per specimen. So mixed samples become tractable, but also automation and big data processing become a much bigger topic than on machines which give you, let's say, one monolithic block of information. So this is what we came up with together with our friends from JEOL. You probably will know them, electron microscopy maker almost down the road from Rigaku in Tokyo. And together with them, we built this dedicated electron diffractometer, which also is now at Northwestern University, among many others. It is has a very highly optimized hardware and software, really dedicatedly designed for micro-ED, and it provides a very integrated experience, the full workflow from instrument control, sample screening, data collection, all the way to structure solution in one cohesive user experience, which does not require any TM knowledge. So if we just schematically look inside, what we see is electron optics beamline built by JEOL. It operates at 200 kV acceleration voltage, has capabilities for this screening for crystal grains in real space, and also a bit higher resolution information. We can vary the detector distance by means of a zoom system, an electron optical zoom system here. So just with a click of a button, we can have very high resolution collection if you want to do, let's say, charge density studies on hard materials, but you can also do proteins. We have X-ray spectroscopy built in for elemental analysis, and so on. We have the High-pix ED detector. It's the same High-pix detector that's on all our X-ray devices. Single electron sensitive, has no background. It's exactly what you would want for crystallography. Now, one key feature is that all of this is controlled from Chrysalis Pro, which is our software ecosystem. It controls every aspect of the instrument, of the measurement process, of the data management, and so on, and will be especially easy for everyone who's worked with a Rigaku instrument before. And we have a sample stage with different kinds of sample environments, and I want to talk about this just a bit because it's also something that's of course quite different from X-ray. So how does it look like if you put a sample into this? So you have these transfer sticks that you see here. It's very similar to a TM with a bit different geometry. Then you have these sample grids that I mentioned. You put them in and you get them into the airlock of the instrument, which will, not that quick as in the video, but within less than 2 minutes, pump down the samples to vacuum level. And that it remains, the sample remains on this stick throughout the whole measurement. It sits on this goniometer, which is outside the vacuum. And now, if you do if you find a good crystal and you do the data collection, this whole thing will just rotate as data is collected and read out by Chrysalis Pro, which already during collection will process the data and get a structure solution for you. Let's say in the best case scenario of the fairly simple samples, often you will have to do some manual work afterwards, but it often works surprisingly well. And because we have this monolithic coupling of the sample to this holder, we can add all sorts of functionality into these holders. So we have holders with electrical contacts for heating to high temperatures, and for electrical biasing. We have motion control, we have thermal coupling to cool them to liquid nitrogen temperature, we have liquid to gas flow systems, whatever you want, that can be integrated in here for different environments. So you're not restricted to just measuring at room temperature in vacuum like back in the old days. The arguably most important one that everyone is using is the cryotransfer system, which is used for hydrated samples or solvated samples. In this case, you freeze those outside vacuum in liquid nitrogen, you load them on this tip of the holder, you close a shutter, which creates a small atmosphere here. So this whole thing here is now cold and now filled with a dry and cold nitrogen atmosphere. And this buys you like 10, 15 seconds to get it into the diffractometer where it gets pumped down and then remains cold and ice-free. And this makes a key difference for your samples. So if you, for example, measure hydrated sugar at room temperature, you'll see it will dehydrate and often the whole crystal lattice will decompose, whereas if you use cryotransfer, it will just totally stay intact. And this is something we do for roughly half of our samples. It's absolutely required. And now just briefly, now that I've spoken a lot about data collection, I also want to talk about data analysis. And with that, I want to get back to this whole story about the dynamical diffraction. So I mentioned already that this kinematical relation between the intensities and the structure factors already gets at least a viable approximation again if you do ED in the modern style. And that it's still an approximation can be seen in R1 values from the refinement. If you do a refinement that actually minimizes this difference, which of course will not converge to something as small as it does with X-rays. So the median is typically like 17% is from some statistics from our labs, and this is what most ED researchers will confirm. Still, this holds well enough easily to get an ab-initio structure solution. This doesn't depend that much on accurate intensities anyway. But what you see is that even though this residual is fairly high, the accuracy of the position of the minimum in the least squares structure refinement is still the correct one. So you still get accurate structures even assuming this approximation. That's totally fine. So these values are not indicating bad quality. It's really just systematically. Still, this wastes a lot of information doing this approximation. There's so much more to electron diffraction, which you only get if you explicitly model these intensities. And this has been championed by the group of Lukács Palatinos in Prague. starting from 2015 roughly, where this is explicitly modeled using a block wave theory, and this brings with it a lot of advantages, like much more visibility of light atoms next to heavy atoms to study protonation. Then, as you see here, if you take this into account, you model that dynamical diffraction also breaks the Friedel-mate symmetry. So IHKL will not be the same anymore as I minus H minus K minus L. And once you model this, of course, you can distinguish between enantiomers, which is extremely powerful for pharma and other applications. And the R values that you get will then, of course, also recover almost to single crystal X-ray levels. You see that here for this tyrosine sample, and you also see that for the two different configurations, you will get different R values and you get the correct enantiomer out of a dynamical refinement. And this is becoming more and more standard in electron diffraction pipelines and gives you still much better results than this kinematic approximation, which often is also just good enough. Depends on your application, really. So where does this help us? Just some use cases. We have plenty of publications about electron diffraction already. We're nearing 60 now. And I can't do justice to all of them now. So I want to refer you to these two webinars where we discuss many of them in a lot of details. Typical challenges where you apply ED are you have small crystals, you have poor crystallinity, only tiny sample quantities, you need a lot of screening, you have mixtures, you have very specific questions about, for example, the stereochemistry, as I mentioned. Also, distinction of salt and co-crystals. Here are just some examples that I like particularly. For example, really impossibly hard structures like this one, which have a low symmetry, where very radiation sensitive and really impossible to solve with X-rays, with very small crystals. This is an interesting one, which highlighted in a pharmaceutical compound that you can quite easily distinguish salts and co-crystals by accurately locating hydrogen atoms due to these different scattering properties, due to this electrostatic potential versus electron density story, which makes hydrogens more visible. You can confidently assign an absolute structure, and you can also really get to cope with really tricky stuff like these low-dimensional graphene structures, which are really just too sensitive and too small to be solved with X-rays. Now, with you guys sitting at Northwestern, of course, I need to mention that the probably so far biggest application for ED is certainly research in porous materials. It has certainly had the highest impact here. It's really a godsend for the MOF community, also for COFs, CIFs, 1D and 2D structure, anything porous where it's hard to grow large crystals, which are radiation sensitive, hard to prepare. And I would say there's a bit of a micro-ED driven research now, because you can explore whole new synthesis pathways, which previously would have been inaccessible because you just couldn't understand what you get in the end. And now this is totally made possible and is becoming a routine technique in this toolkit for MOF research and similar. But there are, of course, many other communities that benefit from it a lot. Now, this is a totally different thing. This is an inorganic catalyst, just as one inorganic compound where you have a typical problem that you have very small crystallites and you have different phases in your powder that will make your powder pattern totally congested and hard to understand. And this is exactly the case where in an electron diffractometer, you collect from a lot of grains and you get the different structures and you just understand what's in there. Something which would be very hard with powders. And of course, you can do pretty much the same or similar applications in the pharma field. You see that here. So this is this is actually the structure of a common drug, and there are several known forms, and there's this form 7, and this could never be solved with single crystal X-ray. It was totally ambiguous data, very poor quality, which then was later on understood better that one reason for this was that this is actually not one polymorph or one form, but two of them, which were never properly distinguished, which could then finally distinguished in electron diffraction. The powder patterns were understood and everything was good. It's quite a nice paper that we have here. And now the final paper that I want to show is, because this connects quite nicely to the final section of my presentation, is this one. It's also about a pharmaceutical, levocetirizine dihydrochloride. It's a common antihistaminic drug that has been administered over decades now, but the structure is unknown because it's so hard to recrystallize for X-ray diffraction. So what we did here, in collaboration with NYU Abu Dhabi, is to get a pill from the local pharmacy, grind it down, and then in the powder pattern mostly see lactose because it's a pill, it's mostly sugar, there's only a little bit of API in it. But then again, in ED, you don't care. You just search for the needle in the hay manually or automatically, and then eventually you just will find the API. And then in a very straightforward manner, we could determine the structure for it for the first time, including the absolute configuration. I'm not showing this here, but here is again one case where we just use this dynamical refinement to confidently get out the absolute structure. So what's the story with this automation that I keep mentioning? Well, on each grid, you have thousands, 10,000s of crystals. Now, they're all different, of course, even though they first look all the same in that they all have different diffraction quality. You always have to look a bit for one that really is the best, and doing this manually can be tedious. Then, like in the case that I've just shown, you often have polymorphs, mixtures, impurities in it that you need to disentangle. And then there are cases like in this one where you have a low symmetry, where it becomes tricky that the tilt range of a goniometer in ED is usually limited because of the small geometry of the instrument, but also because if you have something that's very radiation sensitive, you only can use tiny doses, get small signal to noise ratios, and you need to merge many crystals to get a good enough compound signal to noise ratio for a good structure refinement. And to really get the most out of micro-ED, you really have to understand it as a technique where you use a powder sample and where you understand it as a powder sample as a whole and not only on the basis of single crystals. And in this case, of course, automation becomes a must. So, well, the first part of all of this, of course, to first find the crystals in the first place. You can annotate them manually. This is still what most people do because it's actually not so much work for later steps. As you see here, we also have functionality to do that automatically, just identifying them. I should say that at the moment, this is a major topic to improve this mechanism with machine learning approaches. I would say this is obvious that this is something that machine learning should be used for. So I think, for example, that most experienced practitioners of AD wouldn't have selected this. They would have actually selected this, maybe not this. So even though we have these automated routines and they are good, they are not as good as we think they are right now. So this is a big R&D topic, and luckily we have a great software team with ML experienced programmers who are working on this right now. So once you have annotated them, then you can run automatic measurement. Now this video is accelerated by a factor of 10, I think. So we're not that fast yet. We hope to push it significantly below 1 minute per crystal, including what you see here when the visual display turns like this funky red and blue, which is that the machine automatically centers the crystal on the rotation axis of the goniometer using image processing. This is quite reliable with quite a sophisticated algorithm. It's trickier than it seems, I should say. So this works quite well now. And then once you have all of them, of course, you need to manage this amount of data. We now have powerful features of this for this in our software as well. So we have this results viewer, which has a database where you can store thousands of experiment results from one of those queues, or even what you have on your hard drive already. We have bulk analysis features. What you see here, most importantly, is a clustering of unit cell parameters that you find in measurements such that you can assign each individual grain to one class of compounds with same unit cells, which also will guide you through merging those data sets into compound data sets with high signal-to-noise ratio and completeness, also all built into Chrysalis Pro that will eventually give you the structure. Actually, this figure is from a data set where we did a data collection on a standard clinker sample to just identify the components. This works very well. And in fact, we even found some surprises in there, even in a well-characterized samples like this. Publication is underway on this. But of course, you can also, especially if you have very radiation-sensitive compounds, do those measurements and then merge together those different groups and just get structures from this in a guided way. So that's also fully possible. Finally, what we have now is that in these automated processes, you don't only have diffraction data, but you can also include into this elemental analysis via EDS from each grain. You can get real space images at a nice resolution, and you can also get real space thermography like shown here, where you just watch the crystal rotating and get more idea about its morphology. The video here also that shows how this works. So we can maybe just look at one and then skip this. So it goes on the grain, collects the diffraction data, then gets a high resolution image, and then does another run where it remains in real space. And you get this full morphological information in 3 dimensions, and then get correlative results like is shown here. So you have grains with different diffraction patterns, different morphologies. EDS is not yet included in this image, but the way it works is similar. So you have grains where you get the diffraction signal, but you also get EDS spectrum to identify the compounds. And this was an example sample where we had the same compound with iron or gallium in it, otherwise the same structure. We could, with this, distinguish for each grain what it actually is and put this into the structure solution. Also quite handy for many applications. So let me wrap up. Some take-home messages. Micro-ED has evolved in the last 15 or so years from an exploratory approach to a mature tool, which is becoming standard in many labs to get structures from sub-micron crystallites and solve really everything that's nanocrystalline. Even beyond, I have not talked about pair distribution function analysis and so on, but there's a lot to learn here as well in various environments. And now, in the context of today, I want to highlight that you can also analyze full powders, native impure samples with full structures from everything, and that automation is the essential bit that turns these schemes into high throughput schemes and really make this a powder grain by grain machine. And with a dedicated diffractometer, this becomes not more difficult than any other more conventional techniques. So thank you very much for your attention. Of course, I'm very happy to respond to any questions.
Thank you, Robert. Do you have any questions? Please raise your hand if you have any questions. Yeah, one question. I'll give you the mic so you can hear the question.
Thank you for your talk. When you're reporting quantitative data based off of sizes, percentage of a compound contained, is that based off of how many diffraction spots you're taking, or does the size of the grain matter?
It's a very good question, and I should say that maybe I should improve this slide a bit. So this is not what we measured in ED. This is just the composition that is defined in the standard data. It is a very, very tricky question, and we're at the moment investigating this. I just had a call earlier today about this. It's very hard because you may have a bias, for example, in selecting the grains for grains that have a, let's say, well-defined or good-looking morphology and are in the right size bracket. Or you may have a bias because of varying crystallinity, and so on. So just counting how many grains you find from each type is not necessarily the way to go. Then you could factor in the volume of each individual grain that you found. Maybe that helps. But I think to really get this quantitative, the way to go would probably remain that you identify all the structures, simulate powder diffraction patterns, and fit this against a powder data. This is at least for the moment. I don't know what the future will bring. I guess for some compound classes it will become really quantitative technique. For the moment, I would always combine it with powder.
Any other?
Hi, thanks for the talk. So often when I'm doing this manually, I find that my TEM grids are kind of bent. So I have to, if I want like the full, negative 65 to 65 degrees range of the crystal, I have to go like negative 65 to 50 or negative 65 to negative 50 and then recenter it, then do negative 50 to like negative 20 and then do it in like chunks like that. So I'm wondering with the automation, can the computer like just automatically come up with like a path where it can say, okay, I need to recenter automatically after going through this range and then recenter the crystal, or is it only like it centers it and then just figures out the range of the crystal?
So it depends. Like typically, if the instrument is freshly aligned, you should not have to do this in too many steps. Usually, what the algorithm will do is that it will rotate over the full range, and then you can ask it to set the limits automatically for you based on this. And but usually the reason is not necessarily that it would drift out by itself, but that it gets obstructed, and then recentering by another grain or by grid bar and so on. So recentering won't help you. But if you have a scenario where you really have a runoff of the gonio, which may happen, especially if you go to extreme positions on the grid, which sometimes you just have to do because the center is bent or ugly and so on. At the moment, what we can do and what I would recommend to do is quite simply to start different data collections at different starting angles and then merge them later on. That would be usually the way to go. What we do not implement is an online, let's say, tracker, because that would yield, let's say, quite suboptimal data as a whole. So we're not big fans of that approach.
Thank you.
I'm curious, could you speak to sample preparation? I mean, do grains very often distribute uniformly on the grid, or is there a lot of challenge with overlapping grains?
Well, that's of course it depends a lot on what sample you have. So it can be waxy and sticky and hard to grind down, but usually you find some sort of preparation where they disperse nicely. One thing that often helps to understand at least is that you always use only a tiny fraction of the grid. So preparing them such that you have a gradient of loading density on the grid is often a good idea. So just, I don't know, if, for example, if you load them by touching your powder with the grid and rely on an electrostatic attraction, do it a bit tilted and you get a gradient. That's one way. If you do it with drop casting, do it with multiple drops and blotting runs and so on. It's rare that you don't find any way of preparing it, but sometimes it needs a few runs. But I think with more practical experience for different sample classes, usually these will be less and less. It's not like in cryo-EM where you spend half your PhD thesis in optimizing grid loading.
Thank you.
Thank you. There's a lot of data in the electron diffraction history that error bars are incredibly important and you can't actually make the same assumptions as people make for X-ray diffraction. Have you thought about including the error bar analysis based upon your repeat measurements in what you provide to users, and chi-squared refinement? Because chi-squared and R1 can often be very different with electron diffraction data.
That's a good point. It's I think the underlying problem here is that still mostly just X-ray codes are used for the refinements for electrons. And these, let's say, electron-specific extensions for questions that like this one, where, for example, you need to be more rigorous with the statistics for the lower signal-to-noise ratios you often have with electrons, first need to be incorporated. And we're working quite closely with OLEXsys on this to have new features in OLEX Refine. At the moment, this was more focusing on dynamic refinement, but this is certainly another thing to look into, to have more solid statistical understanding of the data, not just in a chi-square sense. Actually, a good point, but it's only at the beginning